This is a recorded lecture on Chapter 10 from your Essentials of Radiographic Physics and Imaging book. And this chapter actually begins on page 113, where we will discuss the digital image receptors. The best thing to do with this is listen to the lecture. Ideally, you've printed out the PowerPoint and you're able to take notes on it. And also, it would probably help to have your questions out and just kind of use those as a guide as we go through this. So this chapter contains a lot of information. We're just going to kind of skim through and stick to pretty much the basics of this because this will all come up again in your second physics class. So this is just to kind of give you an understanding, a foundation of where we're going in the future with it, not to overwhelm you at this point in time. So this is going to discuss the digital image receptors. And they start off in this chapter telling us that radiography is basically the last of the medical imaging modalities that actually made this transition to digital technology. Multiple other modalities have beat us in that quest for digital, and they reference that it's not a new concept. CT, sonography or ultrasound, nuclear medicine, and MRI have been digital for quite a long period of time. And when we talk about our digital receptors in radiology, there's actually two types of digital receptors. We have computed radiography, which we usually refer to as CR imaging, and those systems use storage phosphors to temporarily store energy that represents the image signal. And then we have direct radiography, or DR, and those systems have detectors that directly capture and read out an electronic image signal. So with CR, you typically have to process that image. You have to take it to a plate reader and process the image. With DR, which is direct radiography, that is pretty much you take the image and within seconds it comes up on your monitor as a completed image. So there's no taking anything anywhere. Like with film, you have to acquire the latent image and then process it. With CR, you acquire the latent image and process it. But with DR, or direct radiography, there is no, you acquire the image and it's processed at the same point in time to where within seconds you're visualizing your image. Kind of like when you take a picture on your phone, you take it and within seconds the image is there for you to visualize and evaluate. Same thing with our DR equipment. When we talk about the different detector types, we're going to start off looking at the CR system, or computed radiography. And the good thing about CR systems is that they can be integrated with existing radiographic equipment. So you don't have to go out and purchase all new equipment and replace everything in the radiology suite. Typically with the CR system, you use your existing equipment, like your tube head assembly. You would have the same tube, the same protective housing, the collimator, ideally the wall bucky, the table bucky, your table. None of that would actually switch out. The only thing that you would have to update or recalibrate is your automatic exposure control, or your AEC, which we have not really talked about yet. We will. That would have to be updated, and any pre-programmed techniques in the anatomically programmed radiography would have to be adjusted, meaning that if you're going from film to CR, you would have to make adjustments in your technique. But aside from technique adjustments and altering your AEC, there's really not anything that has to be changed out. You can see in this image here, this is showing you the plate reader. This right here is a plate reader where you process your image. You can see right here, this is a cassette with a photostimulable phosphor in it. So this is your CR cassette. It gets placed in the plate reader, and then once it's processed, it comes up on this monitor. So these things would actually have to be added to your radiology suite: some new image receptors, a plate reader, and a monitor for you to be able to visualize these. Now that's if you're coming from film. This was pretty much the first wave of digital that we got, was the CR units. All right. When we look at the parts of a cassette-based system, which CR is a cassette-based system, okay, you have a cassette, and inside that cassette you had a photostimulable phosphor, or a PSP plate. You also need a plate reader, and you have a computer workstation. So if we go back for a second and look, this right here would be your cassette, and inside this cassette is your PSP plate. So both of those are contained in this cassette. This is your plate reader, and this is your monitor and your computer workstation, your desktop station that is required in order to visualize that image that you took. So those are the main parts of a cassette-based system: the cassette with the PSP, a plate reader, and a computer workstation. And realize that it is cassette-based, meaning there's something that you take and carry in, just like with film. Film has a cassette with film inside of it. CR has a cassette with a PSP inside of it. As far as our cassette, it is a container that holds the PSP plate. It's typically made of a lightweight plastic so that it's not heavy and cumbersome. It's lined with felt material, and it's backed with a sheet of aluminum. And the purpose of that sheet of aluminum is basically to absorb any X-rays that penetrate the plate. It absorbs those so that they don't exit the plate and potentially expose anyone in the room or the patient. So it is lined with a sheet of aluminum on the back side of the set. If we look at a cross-section of a PSP plate, there are several layers in this plate. Now, I recognize that this looks like it's pretty thick, but this is about the thickness of like a piece of cardboard. Okay, so all these layers are contained in something that is about the thickness of cardboard, or even like our radiographic film. It's about the thickness of a piece of radiographic film. So the layers you have, this would be the top layer, and this is the bottom layer. You have a protective layer that protects the phosphor layer. Okay, your phosphor layer is actually what makes the whole thing work. So your phosphor layer is the heart of the plate, and it actually contains the phosphors. And typically those are of the barium fluorohalide family, and there's also europium in there. So these are the things that are actually going to give off light in response to X-ray, kind of like exactly how Röntgen discovered X-rays. So the protective layer protects the phosphor layer. Then you have a reflective layer that when the light gets released during the reading phase, it sends it towards the photodetector. You have a conductive layer, and then you have a support layer, like the foundation of the PSP plate. So these are all the layers that are found in the PSP plate. And then underneath the support layer, you have like a soft backing layer that actually protects the back side of the plate as well, that is not listed in here. So this would be the front or closest to the patient, and this would be the bottom or furthest away from the patient inside the CR cassette. And again, I'm just showing you these layers, not really going into every single thing in there, just wanting you to understand the concept of how the CR cassette works. Now, these next few slides I'm going to tell you will likely be overwhelming, but I don't want them to be. I'm simply letting you know how CR plate acquires the latent image, but I am not holding you responsible for memorizing all of this stuff at this point in time. It's just to kind of present the concept, which you'll go further into in your second physics class. So what happens is the plate responds to the X-ray exposure, and by plate we mean the PSP plate. So the X-rays ionize the phosphor atoms, all right, in the phosphor layer, it ionizes these phosphor atoms, and about 50% of the electrons get trapped in the conduction band, and this represents the latent image. So it says the quantity and the distribution of those liberated electrons, and liberated means freed electrons, is proportional to the X-ray exposure that was received in each particular area of the plate. And then during processing, the energy of those trapped electrons is released by being exposed to a laser in the plate reader. From there, you typically have in the reader, it has a drive mechanism that moves the PSP plate through the laser scanning process. The optical system is made up of a laser, some optics, light collecting optics, optical filters, and basically those project and guide a precisely controlled laser. You have a photodetector that senses the light that gets released, and you have what's called an analog to digital converter that converts the light to an electron signal, and then the computer processes and displays the image. Now again, these two slides are way more information than I'm actually holding you responsible for right now. I just want you to understand the concept of how it acquires the latent image. It traps the electrons in that conduction band, and then when it's placed in the plate reader, basically a laser scans that, releases the energy, and the energy equates to levels of brightness on your image in response to how the anatomy was when it passed through. Okay, so way more information, a lot of overwhelming. Don't let it overwhelm you. Just take it for what it is. And ideally, you save this PowerPoint so that when you get to this in your second physics class, you have it to go by, which will be a lot, some of these slides will be a lot more helpful then. All right. Now we move on to the DR system, or the direct radiography. And with direct radiography, what happens with that is we actually have right here, this is a picture of what's called a detector array. And the detector array replaces what we currently use or call the Bucky assembly. So with the Bucky, whether it's the wall Bucky or the table Bucky, with film and with CR, you place that cassette, whether it holds film or a PSP, in the Bucky tray, and that's what holds your IR when you make the exposure in a Bucky. Meaning, when you're utilizing the Bucky, it means that your part is above 10 centimeters in thickness, and your KVP, operating KVP, is above 60. With direct radiography, we don't have a Bucky assembly, we have what's called a detector array, all right, and that replaces the Bucky. So this is a picture of a detector array. With DR systems, you have image-forming radiation captured and transferred to the computer from this detector array for viewing at the control panel, and it's almost immediate. And they tell us that with the DR systems, we can either have indirect capture systems or direct capture systems. Okay, so when you work with a DR system, you either have indirect capture or direct capture. And there's actually two forms of indirect capture. All right, so one of the forms of indirect capture uses what's called a charge-coupled device, an X-ray scintillator, and the optics. That is the first form of indirect capture. All right. The second form of indirect capture is actually found on page 116, and that uses a scintillator with cesium iodide or gadolinium oxysulfide as the phosphors. It uses photodetectors, and it uses what's called a thin film transistor array, and that is the second form of indirect capture. So you either have one that has a charged coupled device, a scintillator, and optics, or you have a scintillator, photodetectors, in what's called a thin film transistor array. Again, overload of information, lots of information, lots of acronyms, TFT, the PSP, the CCD. The best that I can tell you right now is I would make cards for those so that you can utilize those for the future. Right now, I just want you to understand what I'm saying and understand that there are two different forms of indirect capture with DR systems, and then we also have what's called direct capture. And direct capture is actually better in the long run. So the indirect capture methods actually cause a loss of resolution. Okay, so there's a loss of resolution with the two that we just mentioned, but the direct capture method avoids that problem of loss of resolution by not using a scintillator. Okay, so the direct capture method uses a photoconductor and the TFT array, which is the thin film transistor. Okay, so with DR systems, the direct capture method is the better of the methods because there's not a loss of resolution. With the two forms of indirect capture, there is a loss of resolution. Okay, and that's with the DR systems. So we first had talked about the CR system. Okay, with the CR, and then we just now have discussed the DR systems. Excuse me. All right. As far as the image acquisition, the extraction and the processing and the display, when they talk about acquiring the image, it's how do you capture the latent image? And then how do you extract that latent image and process it? And how is it displayed? So with our digital receptors, both CR and DR, the acquisition is, you have a couple things that come into play. You have what's called a histogram. And your histogram is a graphic representation of your data set. And this is an example of a histogram. So this tells you the pixel value with regard to number, the signal of the pixel value, and this is how many of them there are. So again, you have an X and a Y axis. And your histogram is basically a graphic representation, so a graph, an X and a Y axis, of all the information that is in one exposure. So let me look real quick for something to give you a little bit better understanding of how that, a better description, I guess, of what that histogram actually is. Okay. Sorry about that. Let's see, I can figure out where I put that. It's a graphic representation. Chapter 6. Hold that thought. Don't give up on me. And you know, when you're looking for something and you know darn well you're not going to find it because you're actually looking for it, that's exactly where I'm at. Okay, I will have to give you the definition that I typically use once we're in the live, because I'm not going to find it right this second just because I am looking for it. But it's basically a graph with an X and a Y axis that represents the values that are in your digital image, and those values correspond to the brightness levels on your image. So when you have a histogram, basically, when you select what you're going to image on the control panel, you have to tell the system that you're going to take a picture of a chest or an abdomen or a hand or a femur. Whatever you're going to image, you tell the computer that's what you're going to image. And the computer has a histogram, meaning that it knows with what you've selected, it knows what it should look like. So when you give it your information, when you make the exposure, the system takes what you've given it and it compares it to the histogram that you chose, and it analyzes it. And that's how it attempts to make your image look like it's supposed to. That's why we constantly say that when you have those point processing functions of automatic rescaling in the lookup table, and I say that if you're over or underexposed, that the image can appear with acceptable brightness and contrast, but it doesn't mean that you didn't over radiate or that there's not quantum noise exhibited. So that histogram, the computer has a histogram that's based on a diagnostic image. And it takes the information that you're giving it and it compares the two so that it can attempt to make it look like the diagnostic stored histogram as best it can. All right. Now, the only other thing I want to mention at this point with the histogram analysis is that it is possible if you select the wrong exam, like let's say you were taking a chest and you accidentally hit abdomen. It used to be that when the system got the information you were sending it, if it completely did not match at all, it would throw a histogram analysis error saying, wait a minute, I know what you're trying to get me to look like, but what you're giving me is nowhere near that, and I can't do it. So it would throw a histogram analysis error, and you would have to repeat the image. But what they've done, because that has happened so often, what they've done now in the computer systems is they've made it where when it takes the information from your exposure, it stores that as raw data so that you could back out of that and make the proper selection for a chest and reprocess that image without losing that original raw data. It used to get rid of it. Like once you processed it, you couldn't go back to the beginning again. But they've made adjustments in the system now where you actually can go back and reprocess that image you've given it so that the patient is not having to be re-exposed because of our error in selection. So it still might throw you a histogram analysis error, but it's not going to be where you don't have to re-expose the patient. You can still save it by going back to the raw data, correcting your mistake, and reprocessing that image, right? So I just want to make mention of that while we're here. All right. Now, as far as acquisition with the CR systems, so again, this is CR we're talking about. Very simply, this is how it extracts it. This is what takes place in the plate reader. We have a laser, we have, remember, the optics and the filter and the photo detector. Okay, so when this is in the plate reader, it scans the conduction band, the PSP plate that you put in there, and this is how it actually acquires the latent image and it extracts the latent image. All right, and that picture was actually on page 118. So it tells you that as the electrons get liberated by the laser, they return to their shells and release excess energy as light that is directed to the photodetector through a fiber optic bundle. Okay, so when it scans, if we look back, it releases these electrons, which basically are released and then they are detected by the photodetector. And from that point, the photodetector amplifies the light and converts it to an electronic signal, and it passes through the analog to digital converter. Okay, So it takes that signal, it converts it to light, and it passes that on and digitizes that latent image that you took. This is how it's extracted. All right. Again, I know it's more information than you need, but I just want you to attempt to understand, or at least hear, how the process works. So the electrons that were released by the laser, they return to their shells. They release excess energy as light. Right, because we know that anytime it goes back and it goes back to its shell level, it has to give off any excess energy. So it gives it off as light that's directed to the photodetector. That photodetector amplifies that light and converts it to an electronic signal. That signal passes through the analog to digital converter, and it gets digitized. And when that takes place, the analog signal gets divided into a matrix. Okay, now it's starting to sound a little bit more familiar, I hope. So the matrix determines the resolution, the spatial resolution of your image. So the larger the matrix, we've said there's more pixels, those pixels are smaller, and your resolution is improved. All right, so when it sends that signal, it converts it or divides it into a matrix. The matrix size determines your spatial resolution, because when you have a larger matrix, you have more pixels, and those pixels are smaller, and your spatial resolution is improved. And they tell you that the scanning of the plate results in a continuous signal being sent to that photodetector and onto the analog to digital converter for sampling and quantization. Do not like that word. So the image gets digitized by both location and intensity. Okay, so the location helps with the spatial resolution, and the intensity or quantity is what your grayscale is. So the grayscale gets assigned during the process of digitizing the image. The bit depth, remember we talked about from the center of one pixel to the center of the correlating pixel, the one right next to it. The bit depth is available as the grayscale. And it says the number of photons detected within that pixel value determine the shade of gray that it displays. And then the computer puts the image data through a series of steps, and it creates that displayed image that we end up seeing on our workstation. All of that takes place within, it typically takes to process a SAR plate is about 90 seconds. So it's about the same length of time as when we used to process film. All right, now the DR systems, how does that work? For the DR systems, there's 2 indirect methods and 1 direct method, right? And they go into that same thing of what the indirect method uses and what the direct method uses. And we don't have to go into that as much in depth, because again, this is just foundational. So we said that one method used the oh my goodness, I'm getting confused. One method used the cesium iodide as a scintillator coupled to a charged coupled device, or the CCD, by the bundle or the lenses, right? And then it went through the analog to digital converter. Whereas the other method used cesium iodide or gadolinium oxysulfide coupled to a photodetector and that thin film transistor. Okay, so with the DR, it can use either one of 2 indirect methods or the direct method, which is this, which uses amorphous selenium, a photoconductor, and a TFT array. Okay, so there's 3 ways that the DR system can extract that image. And it totally depends on what equipment you have in your department or has been purchased. And they tell you that regardless of which one you use, one of the 2 indirect or the direct capture all three systems at this point go through the same image forming steps. There's a histogram that gets analyzed. So you create the histogram with what your exposure was. It's analyzed and compared to a stored histogram that represents like a diagnostic image. The exposure field gets recognized and the histogram analysis takes place. This is where your automatic rescaling, where it determines like your predetermined level of brightness is attempted to be matched. Your lookup table where the contrast is also attempted to be matched at this point, because these are point processing functions. So they take place during processing before you visualize the image. But realize it says that with these systems, with the DR systems, only the detector pixels that were exposed contribute to the image. Now, why is that significant? Because with the DR systems, only the ones that get exposed contribute to the image, which means it's very important, probably more so important, that we collimate and only expose to include the area of interest, not to include the unnecessary area, because those pixels that get exposed contribute to the image. So you want to limit what doesn't get evaluated in the image. I mean, you don't want wasted space is pretty much the way to look at that. So you want to collimate, and it's way more important with DR systems versus CR or film. It's important regardless, but I'm saying with the DR systems, it's vital that we collimate, right? And then with the digital receptor, their response to exposure is very wide. We've said in the past that it has a wide dynamic range, meaning the range of exposure intensities that IR can respond to and use is huge. So ultimately, what that means is that the digital receptor can respond to exposure levels much lower and much higher than film could, and they get processed to display them as visible shades of gray. That's why there are so many shades of gray in a digital. You don't really ever get black on digital, and you do get white, but you're hard pressed to get really, really, really black on a digital image. You can get all different kinds, thousands of shades of gray. And they tell you that because of this, because it can respond to low and high exposure, the result is that you end up capturing more anatomy, and you're able to display that anatomy that's been captured. So digital has the capability to not only capture, but display far more information than film ever did. Probably more so than CR as well, but definitely more than film. All right, so most of your digital images do appear very gray when you look at them. Now, just to mention the point processing functions, these point processing functions take place before your image gets displayed. So before you see it, during that histogram analysis, when it's comparing what you gave it to what a diagnostic image should contain, it goes through automatic rescaling, which adjusts your brightness in the image to appear appropriate. And it also applies the lookup table, which adjusts the contrast or the visible differences in brightnesses in your image. So both of these things are considered point processing functions, and they take place prior to you seeing the image on the monitor. All right. The post-processing functions that we've talked about before, those are computer software operations that allow not only the radiographer but the radiologist to manually manipulate the displayed image, meaning you adjust the window level and adjust your brightness, and you could adjust your window width and adjust your contrast. All right, so they talk about the window leveling function allows you to expand any region of the grayscale to one that can be seen and differentiated, meaning you have the capability to manipulate your image after you see it. But realize that it tells you overuse of those functions can negatively alter your digital image data, meaning there comes a point where you're not able to go back. So we have to, as technologists, be very careful with what we actually manipulate, because at some point the radiologist is not going to be go back, and that limits him or her in what they can evaluate on the image. So some facilities, I've told you in the past, don't allow the technologist to make those post-processing manipulations. And that is, again, window leveling, adjust your brightness, and adjusting the window width, adjust your contrast from low to high contrast. And window leveling, remember when you raise the window level, you decrease brightness. And when you lower the window level, you increase brightness. When you make a wide window width, you have lower contrast, longer scale. And when you make a narrow window width, you have higher contrast, shorter scale. And realize too that with these digital systems, digital radiography uses what we call a 14-bit dynamic range, which equates to 16,384 different and distinct shades of gray. Okay, so completely like mind-blowing, because remember, the human eye can only appreciate 30 to 32 shades at a given level. Okay, so when we use that 14-bit system and it can capture 16,000 plus shades of gray, when your eye can only appreciate 30 to 32 of them, you're capturing way more than you're able to even comprehend by looking at. And again, that's a trained eye. The radiologist can probably see far more shades than even a tech can, but a tech could far more than just a lay person could as well. All right, let's talk about the exposure that is given to the receptors and to the patient. So when we talk about the digital receptors, we have what's called exposure indicators. And in CR systems, computed radiography, the exposure indicator represents the exposure level to the PSP plate. So it's capturing how much radiation was received at the PSP plate inside the cassette. But those values are very vendor specific, meaning that Fuji, Philips, Konica use a sensitivity number or an S number. All right, and they tell you that the value is inversely related to exposure to the plate. That's neither here nor there, but just recognize those three companies use what's called a sensitivity number. Carestream, which would be Kodak, uses exposure index numbers, and the values related to the exposure to the plate, and the changes are logarithmic. But AGFA, which is another company, uses actually logarithm values. So I've said to you before that these are not, they are not, blank, meaning if you use Fuji equipment and Carestream equipment and AGFA equipment, you're going to get different numbers. So they're not, goodness, I cannot think of the word I want. They're not equal across the board. They're very vendor specific. So there's no, they're trying to make it where everybody uses the same system. They're trying to make it where everything is the same, so that no matter what equipment you work on, you could understand the amount of exposure that was given to that plate, which if you figure the amount of exposure given to the plate, that's not the amount that was given to the patient, because it's already passed through the patient. So this is only exposure to the PSP plate inside the cassette. But the value is different depending on what kind of equipment that you are working on. All right. So they're trying to make them all the same, but to date, they're really not equal at this point. And they reference that with the CR systems, you want to use the exposure indicator as a guide for your optimum technique. This is where I typically tell you guys to go green. Okay, tell you that if the value is within the acceptable range, then your post-processing functions, your window leveling and your window width, will not degrade your image. So if you're within that acceptable range, whatever you do to the image after the fact is not going to take away from the image. But if the exposure is outside the acceptable range, then those post-processing functions are not going to correct for improper receptor exposure. And what can happen is you end up with a noisy image or a non-diagnostic image. So meaning if you have an image that did not have enough exposure, you were on the negative side and it was like negative orange or negative red, you are going to exhibit quantum noise, and there's nothing that adjusting the window level or the window width is going to do to help you. It's just not going to happen. You're going to have to re-expose that patient. Okay, so if you're in the acceptable range, then post-processing is not going to degrade your image at all. But if you're outside the acceptable range, then any post-processing is not going to counteract what you did wrong to make yourself outside the acceptable range. And they reference that for a CR system, the histogram analysis is the basis for determining the EI value. So remember that histogram analysis, it compares it to a diagnostic image of the same thing that you're exposing. So that's where the baseline is for the EI value in a CR system. With a DR system, they use what's called a dose area product or a DAP meter, and that indicates the exposure as well for the DR systems. But the DAP meter is actually a measurement of exposure in air, and that DAP meter is found in the collimator. Okay, so the DAP meter measures the amount of radiation that exits the tube, and then it also calculates the dose that was given to the image receptor so that it can calculate the anticipated dose to the particular patient for that exposure. So the DAP meter is specific to DR. It's found in the collimator, and it says the DAP value actually depends on the exposure factors in the field size, and DAP is expressed in centigrade meters squared. So it reflects the dose to the patient and the total volume of tissue that gets radiated. So with DR imaging, you can actually tell how much radiation dose your patient received. With the EI values, it tells you how much radiation your PSP plate received, which is kind of indicative to how much your patient got. But with the DAP meter, way more specific with regard to patient exposure. Standardized, that was the word that I was looking for a few minutes ago. So there is no standardization of exposure views yet. They are working on standardizing those so that they're the same across the board, regardless of what equipment you work on. But in this particular portion where they talk about the exposure index and the target exposure index and the deviation index, these three terms are important to us because the exposure index represents the exposure at the detector relevant to the region that you're imaging, and it's defined by the signal to noise ratio. Remember, the signal to noise ratio was the amount of signal or the strength of the energy of the photon in relation to the noise that is present in your image. And we typically want an optimal signal to noise ratio, but ideally a high signal to noise ratio is better than a low signal to noise ratio. So your EI represents the exposure at the detector. Then you have what's called your target exposure index, which means that your target exposure index is what would be ideal on a diagnostic image. So it's the target reference obtained from a properly exposed IR. So your target is what you, ideally when you're trying to go green, it's what would give you 0, right dead center in the green. If you had properly exposed it, that would represent 0. And the deviation index is how far does it deviate from the target exposure index. So if it's more exposure, it's going to be a plus number, and you're going to go to the right of the 0. And if it's a negative, meaning there was not enough exposure, it's going to go to the left of the 0. Okay, so you start out green and you have an acceptable range, and then it goes yellow, orange, and red. And if you're on the plus side, it means that there was more exposure than necessary. The negative side means there was less exposure than necessary. And depending on your deviation index, that'll pretty much tell you if you have to repeat the image or not. Usually when you're, yellow, you might be able to get away with it. Anything in the orange or red, you're probably going to have to repeat on the negative side. If you're on the plus side and you've done that, it just means that your image is likely acceptable, but you've over-radiated your patient. Okay, so those three things, exposure index, target exposure index, and deviation index, are important. The signal, the DQE, I'm sorry. Just to say the signal to noise ratio, because that is an important term for us to know. Realize that we've talked before how there's a certain amount of noise that's inherent in the system, and that's considered acceptable because you can't override that because it's in the system. But you ideally want an optimal signal to noise ratio. Okay, so to kind of simplify that, pure signal is your mass. It's the quantity of photons. And your noise are fluctuations in your brightness that don't represent true information of the patient. So anything that is not an X-ray photon that interacts with matter, like scatter or quantum noise, that is a representation of a lack of, or that represents your noise. So you're comparing the amount, the quantity of photons to how much noise is in that image. So a high SNR is actually good compared to a low signal to noise ratio. But ideally you just want optimal. You want it to be spot on, proper amount of radiation to the patient without overexposing them, and a minimal amount of noise in there. DQE, or detective quantum efficiency, is how well the detector absorbs the X-ray photons and converts it to an accurate or optimal image. All right, this says that it's an expression of the radiation exposure level required to produce an optimal image. And it's how well does that image receptor convert the exposure into a quality image. I think I had said to you, how well does it take the subject contrast and convert it into radiographic contrast? So the higher the DQE, remember we talked about the higher the DQE, you need less radiation exposure in order to produce an optimal image, and that would give you less patient exposure. So increased DQE, you need fewer photons to create the image. And if you have it too high, though, it can also cause mottle or noise. But if it's too low, then that means you're using a lot more radiation to achieve the image versus something with an increase in DQE. And this is a measurement of your IR, okay? And the DQE actually predicts your patient dose. Like, it can pretty much tell you if your dose to the patient is going to be high or low based on your image receptor DQE. The image noise, again, any fluctuation in brightness that are not represented by anatomy. So it could be artifact, pathology, anything that is not represented represented by actual anatomy. Fluctuations don't represent signal changes. So any fluctuation that doesn't represent actual signal can be considered quantum model or quantum noise. It could be scatter. Okay, so image noise and model can be used interchangeably because both scatter and model are considered noise, meaning it's an undesirable fluctuation in the image brightness. And they reference too that electronic components of a digital system do contribute undesirable noise. And they show you these are two L5-S1 spots on a patient, meaning where the fifth lumbar vertebrae meets the first sacral segment. All right, so this first image, this picture A, they're referencing that that has excessive noise because there was insufficient mass used. So this represents quantum noise. Remember we said it's photon dependent, and there were not enough photons in this to exit the patient to actually make an acceptable image. So it appears grainy or mottled or speckled. But picture B, they did the same part, but they used sufficient mass. Okay, so there was enough photons to create this image so that there's no graininess, there's no mottle, there's no very, very little noise in this image compared to this image. Okay, so image noise, again, not a good thing. The primary factor that influences contrast on your digital is your lookup table. Okay, and your lookup table, or your LUT, is a histogram of luminance values or brightness values. And basically those are used to assign the grayscale values in the image. And the purpose of the lookup table is to keep the contrast consistent. Okay, again, the lookup table and the automatic rescaling are point processing functions that take place before you see the image. So it's not something you control. It's computer programming built in while the processing is taking place. Those two things occur. All right, the modulation transfer function, that is the system's ability to preserve the signal contrast. All right, we talked about the system and how it has the ability to resolve a small object. And ideally what you're trying to do is have the system resolve that object and represent it as separate and distinct. So they talk about how the modulation transfer function is limited on one side by the noise and on the other side by the contrast. So the pixel size is the end-all determining factor, because remember, when you have smaller pixels, they're responsible for less information, which means that you have better spatial resolution. Okay, so anytime your pixel size is small, your spatial resolution is improved. So they reference with the modulation transfer function, if you had less noise and an increase in contrast, it would allow that the smallest object would be able to be distinguished. But if you had an increase in noise and low contrast, then the object is not as easily recognizable. It doesn't stand out as well. So again, it's how well does it convert the subject contrast to the radiographic contrast. And an example of that would be, imagine you're looking at a mammogram and there's a breast nodule. In that mammogram or in a chest x-ray, it's likely that you're going to see that nodule because it has higher contrast. But if you put that same nodule in the abdomen, which has much lower contrast, more shades of gray, then it would be very hard to distinguish that nodule from all the other abdominal anatomy. It would possibly be overlooked. But if it was in the mammogram or in a chest x-ray, it's more likely to be seen based on everything around it. Okay, so how well does that small anatomy actually stand out? With the digital receptors, again, they are much more sensitive to scatter radiation and low level energy. So when you increase the KVP on your exams, it increases the opportunity for Compton scatter to be produced. All right, since they are so much more susceptible to scatter and low energy radiation, it's important to use the appropriate KVP, to collimate appropriately, and to utilize a grid if necessary. But remember, we've talked about the fact that there is virtual grid software, because anytime we use a grid, we have to utilize the grid conversion formula, meaning if you're going from no grid to a grid or changing between grid ratios, you have to alter your mass value to compensate for the loss in quantity of photons striking the image receptor. So now there's software where you don't have to actually use a grid, but the software goes in and removes those low-level energy values from your image like you used a grid, but there's no change in mass requiring the patient to have more exposure. You actually can use the same exact exposure as you would without a grid, but the software is designed to pull those low energy values out. So your appearance on your image is like you used a grid when in fact you didn't. And that, I think, is going to be something up and coming, where most facilities are probably going to move to that because of the fact that it lowers patient dose. So the two ways to effectively control scatter radiation and its effect on your image is to collimate and either utilize a grid or utilize grid software. The image processing errors that degrade our image clarity, things that can take away from that spatial resolution or the sharpness, you have to pay attention to your EI values as an indicator of proper exposure. Like, you really want to attempt to go green. You also want to look at any factors that can result in throwing a histogram analysis error. And you always want to evaluate proper positioning in your tube, part, and receptor alignment. Meaning you have to kind of double check before you make the exposure, because there are image processing errors that can take away from the image quality, and some of those you can control, some of those you really can't. So can you control looking at the EI value and using an appropriate technique? Absolutely. Can you, if it throws a histogram analysis error, you can see what it has issue with, and you would want to review that so that you could effectively not do that again. And as far as proper positioning in the tube and the part and the IR alignment, that is absolutely something that is within the technologist's control. It's only in the technologist's control. The last portion, they talk about quality assurance and quality control. The biggest takeaway is that when you're talking about quality assurance, it's monitoring people. It's monitoring the techs and maybe their repeat rate, or how long the wait is in radiology, how the turnover is. Whereas quality control monitors equipment. Okay, and I try and remember that, because you can control equipment, you really can't control people. So quality assurance monitors people, quality control monitors equipment. All right, and they reference that with digital imaging, quality control tends to focus on the display monitors in the viewing environment, since that is ultimately the most important aspect of the digital image, is where's the radiologist reading, and how is his monitor, what kind of lighting does he have, is there a lot of ambient lighting, and that all goes back to the AAPM, which is the Advanced Association of Physics and Medical Imaging. It's report number OR-03. Let me see if I can. AAPM. I feel like I should know that, but it's just escaping me. We will have to look that up and discuss that, because it's not coming to me right off. But that is in their report evaluating the viewing of the radiologist and the display monitors. They reference that some of the tests can be performed by a quality control radiographer. There used to be a post-primary exam in quality control, meaning that you could earn the initials QC behind your name. They have since done away with that, but if anyone has those initials, it does not mean that they have to get rid of them. It just means that they're no longer offering a registry in that particular not even modality, but specialty. So there is no more thing as a quality control registry, but there are several people out there that actually already have it, and they can maintain that. And then they reference that there are also, not only the radiographer does testing, there can be additional tests performed annually by a medical physicist as well. Okay, so all kinds of quality control factors and QA factors go on to pretty much improve patient care and improve the process that radiology provides for the patient. Not only patient care, but the weight factor, the repeat rate analysis, things like that they can evaluate, monitoring the equipment, making sure that it's working appropriately. All those kind of things come into play, and there's testing that is done weekly, monthly, annually, all kinds of testing. And in the book, they do reference a lot of those tests that take place and the time factor in which they take place. The last thing, the PACS system and the DICOM system. PACS literally stands for Picture Archiving and Communications System, and it's basically a network for communication between the image acquisition modalities, the display stations, and it also plays a part in storing those images. And DICOM is Digital Imaging and Communications in Medicine, and it's a common language used by different systems in order for them to communicate. So PACS and DICOM definitely are a part of our field. The PACS system is something that we use as far as when we, when you take the image in the room and it's showing up on a specific display station, when you send that information to the radiologist, it goes through PACS, and then it also is stored on PACS, and those are usually backed up nightly, minimally. And then DICOM is just a way for the different systems to communicate among themselves. All right, and both of those can be found on page 125 and 126. All right, and we don't go heavily into PACS and DICOM, again, not right now, just understanding what they stand for, but not so much in your future classes. They go into it a little bit more, but not a whole lot. Right? There are PACS administrators. There are separate schooling for PACS. I feel like in order for you to go into PACS, you would have to be very computer literate and knowledgeable. And it's a whole different field. I mean, it really doesn't, it has to do with radiology in the fact that we utilize it, but it's almost like being a tech and then going to be an IT person. They're completely separate. Okay? All right, so that brings us to the end of chapter 10. Ideally, if you have any questions or comments or concerns, you've written those down, and we can attempt to clear those up when we meet live. But again, remember that some of the concepts presented in this PowerPoint are far more than what you need to know at this point. It's just to present the information to you. So the question outline tends to do a good job at just keeping it to what we need to know right now and giving us just a basis and a foundation to build on in future classes. All right, well, if you have those questions, make sure to bring them so that we can clarify anything that you tend to be confused on. And until then, thank you so much and have a good day.